Welcome to another explainer. Today, we're diving into the epic 4.5 billion-year biography of our home, planet Earth. It's a massive story of chaos, transformation, and a very delicate balance.
On our agenda today, the Goldilocks planet, Earth's violent origins, the planetary engine, shields, oceans, and seasons, the evolution of life, and finally, Earth's distant future.
Chapter 1. The Goldilocks planet. What makes Earth unique?
Just look at that stunning blue marble. Earth is literally an ocean planet, the only one in our entire solar system known to have liquid water right there on the surface. But here's a crazy thought. While oceans cover 71% of the globe, all that water is actually just a paper-thin film compared to the sheer massive bulk of the planet itself. Still, this vast global ocean averages about 3.6 kilometers deep and holds roughly 97% of all our water reserves.
Now, let's contrast that with our closest neighbors. When the solar system formed, Venus, Earth, and Mars all started out with pretty much the exact same building blocks. But while Venus turned into this toxic, super-pressurized greenhouse, literally hot enough to melt lead, and Mars lost its atmosphere to become a frozen, thin-air desert, well, Earth settled into this perfect Goldilocks balance. We ended up with exactly the right temperature, the right atmospheric pressure, and just enough mass to hold on to our liquid water.
Chapter 2. Earth's violent origins, born from chaos.
Because, our home wasn't always this peaceful oasis. Around 4.54 billion years ago, gravity pulled swirling gas and dust from the solar nebula together to form Earth. And during this early period called the Hadean Eon, our planet was, quite frankly, a hot, molten hellscape. Heavy metals like iron and nickel actually melted and sank straight to the center in something called the Iron Catastrophe. And then starting about 4.1 billion years ago, Earth just got absolutely pummeled by a relentless asteroid shower known as the Late Heavy Bombardment.
During this incredibly violent early era, scientists think a Mars-sized object named Theia slammed head-on into the young Earth. It's called the giant impact theory, and it suggests this massive collision blasted a huge ring of vaporized rock into orbit, which then rapidly clumped together to form our single, enormous moon. And, as we'll see in a bit, that moon became absolutely crucial for our survival.
Section 3. The planetary engine, Earth's internal structure.
As the planet's crust eventually cooled down, those heavy metals that sank to the center ignited an immense, incredibly powerful engine deep inside. So the big takeaway here is that Earth is a dynamic, living machine. If you were to slice the planet wide open, you'd find 4 main layers. At the very center is the inner core, a solid sphere of iron and nickel under so much pressure that it stays completely solid even at 5,400 degrees Celsius. To put that in perspective, that's roughly as hot as the surface of the sun. Surrounding that is the outer core, which is a fluid layer of liquid iron and nickel. Above that sits the thickest layer, the mantle, made of hot, viscous rock that slowly flows, kind of like thick caramel. And finally, we have the super thin outermost crust, which is cracked into rigid tectonic plates.
All that intense internal heat creates solid-state convection currents in the mantle. Basically, hot rock rises, cools off, and sinks back down. It acts just like a giant conveyor belt, dragging those rigid crustal plates right along with it. This is the engine of plate tectonics. It's continuously destroying and recreating the planet's surface, pushing up massive mountain ranges, tearing open volcanic vents, and literally moving the continents. Actually, fun fact, they move at about the exact same speed your fingernails grow.
Section 4. Shields, oceans, and seasons, protecting the planet.
Now let's see how that incredible internal engine powers the defenses we need to sustain complex life. Deep down in that liquid outer core, the churning motion of all that electrically conductive iron and nickel generates a massive electromagnetic field. This is Earth's magnetosphere. Without this invisible magnetic shield, our fragile atmosphere would have been completely stripped away by charged particles blasting in from the solar wind. Seriously, think about that. Without this shield, the air you breathe and all the life you see around you simply wouldn't exist. We'd basically look like barren Mars. Safely shielded by that magnetic field, it actually took Earth 3 tries to get our atmosphere right. First, we quickly lost a really thin, primordial envelope of light hydrogen and helium. Then, as the planet cooled, massive volcanoes outgassed carbon dioxide, ammonia, and water vapor, cooking up a thick, greenhouse-heavy second atmosphere. Finally, as life emerged, the magic of photosynthesis transformed all of that into our third atmosphere, giving us the exact breathable air that's filling your lungs right now.
As the early planet cooled beneath that thickening volcanic atmosphere, massive amounts of water vapor finally started to condense. And then it rained. And it didn't just rain for a weekend. It rained for millions of years, filling up the low-lying tectonic basins and creating our vast global oceans. And because Earth was sitting at just the right distance from the sun, where the solar intensity is only half of what Venus gets, that water was able to actually stay liquid instead of just boiling away. Today, our atmosphere maintains a very precise, life-sustaining chemical balance. It's exactly 78% nitrogen and 21% oxygen, with just a tiny 1% sliver of trace gases like argon and carbon dioxide. This specific mix is just the right thickness to regulate our global climate, keep the surface nice and warm, and even burn up incoming meteoroids before they hit us. Plus, the gravitational pull of our moon is absolutely vital here. Remember that chaotic collision we talked about earlier? Well, the moon it created acts as an anchor, stabilizing Earth's wobble and locking us into a consistent 23.4-degree axial tilt. That tilt is everything. It ensures we get predictable, life-sustaining annual seasons as different parts of the globe angle toward the sun. Without it, we'd have these wild, catastrophic climate swings that would probably sterilize the whole planet.
Section 5. The Evolution of Life, a Biological Transformation. With that perfect physical environment finally locked in, biology completely took over and changed the planet itself. Life first kicked off in those warm, early oceans roughly 3.8 billion years ago as simple, single-celled organisms. Then, right around 2.5 billion years ago, cyanobacteria started doing photosynthesis, pumping massive amounts of oxygen into the air during the Great Oxidation Event. This fundamentally altered Earth's chemistry. Fast forward to 540 million years ago, and we hit the Cambrian explosion, where complex, multicellular animals just rapidly diversified. And eventually, after a massive asteroid wiped out the dinosaurs 66 million years ago, mammals bounced back, evolving all the way down the line to us.
Section 6. Earth's Distant Future, the Final Chapter.
But the biography of our living machine is still being written, and nothing in the universe lasts forever. As our sun ages, it's burning through its hydrogen core and slowly becoming brighter and hotter. So as the sun's energy output cranks up, it's going to gradually push the solar system's habitable zone, that perfect orbital band where liquid water can exist, further and further outward, slowly leaving Earth behind in the heat. The timeline for our planet's future is pretty dramatic. In about 1 billion years, all that increased solar energy will trigger a runaway greenhouse effect, causing our oceans to evaporate entirely. Then, in roughly 5 billion years, the sun is going to run out of hydrogen and start swelling up into a massive red giant star. And finally, in about 7.5 billion years, that expanding red giant will completely absorb the Earth, ending its physical existence once and for all. Which brings us to a really profound realization. Our planet's perfect, beautiful balance of water, breathable air, and churning tectonic engines is incredibly precious, but ultimately, it's temporary. So when our shields finally fail and the sun expands, it forces us to look out into the cosmos and ask the ultimate question. Could another world out there ever take Earth's place? Thanks for joining me on this explainer. Keep looking up and keep asking questions.